Hello, this is introduction to the course MECE E4501, which is geometric modeling. My name is Rajan. I go by Rajan. I would not try pronouncing my first name. This course deals with geometric modeling, and in particular, the modeling of surfaces and curves in a geometry of a geometric object. But the course actually goes beyond that into doing representation and manipulation of surfaces and dealing with surfaces and curves that come up in engineering problems. The textbook we use in this course is called Shape Interrogation for Computer-Aided Design and Manufacturing. It's by Professor Patrikalakis, who is from MIT. He teaches a similar course at MIT, and you can look up that website for some more information. What we cover in the course is the first few chapters of the book. It starts with the issue of representation of curves and surfaces. I'll get into a little more details there. Then differential geometry of curves and differential geometry of surfaces. And then we consider a bunch of other topics. But these are the main topics, and we consider applications and some material from the remaining chapters. But the bulk of the focus is on the first three chapters. We start the course with study of differential geometry of curves and surfaces. The differential geometry deals with the calculus of surfaces. It deals with the issue of what is the curvature, what's the torsion, how do you characterize a curve in three-dimensional space. And then later on, we move into differential geometry of surfaces, which deals with the issues like curvature, Gaussian curvature, and various things called first fundamental form and second fundamental forms. The mathematics which underlie these subjects, the differential geometry, really dates back to the end of 19th century. It goes from around 1850 to 1900. When the mathematicians developed this mathematics, they did so because it was beautiful and elegant and intellectually beautiful. But in the later part of 20th century, when people started building CAD systems, they realized that this mathematics provides the core foundation for the CAD system. So one of the things I emphasize in this course is that this mathematics is not only beautiful, but also very useful. And one of the things we talk about is how they are useful, why they are important. This part of the course involves quite a bit of calculus, so I would assume you are familiar with calculus, particularly with partial differentiation, and also quite a bit of vector analysis, so I assume you are familiar with vector analysis. Most mechanical engineering students have taken calculus 2 and 3, and that will provide more than enough background for these subjects, and also you are familiar with vectors. And if you have forgotten some of it, by the time you have done some of the problems in this part of the course, you will become proficient in that part of the course. To get in addition, we talk about the representation of curves and surfaces, and this deals with some other part of the geometry. Part of the issues that come up here come under the realm of algebraic geometry, which is another branch of mathematics which evolved in the late 19th and early 20th century. And when they developed it, it was considered a beautiful mathematics, not particularly useful. But I remember I started working in this area about 28 years ago. And when I started working, and with a group of us were trying to solve some problems, we realized that these problems had been solved in the 19th century by mathematicians. So we called a mathematician, asked him if he would come and give us a series of lectures on the specific topic, and he was surprised because he didn't know that his branch of mathematics was useful, and he was happy to come and talk to us. So again, these deal with some mathematics which is beautiful, but it became valuable to us because we needed it to develop the CAD system. So when I was involved in working on the CAD, we had to learn some of that mathematics. We won't get too much into the mathematics. We won't try to prove the theorems. Some of those are fundamental theorems. Rather, we will just acquire enough knowledge to be able to understand why CAD systems are built the way it is. And the latter part of the first chapter deals with subjects of how you represent curves and surfaces in today's computers. Interestingly, this part of the mathematics evolved in the last half of 20th century, almost 100 years after the earlier part evolved. And that's because these mathematical techniques were developed specifically to represent information on computers. And since computers came in the late 20th century, that's when people started developing these things. These subjects involve things like splines, Bezier surfaces, and base-spline surfaces. And finally, in the end, we'll learn about nerves, which is non-uniform rational B-splines. Those are and nerves are standards in the computer-aided design and computer-aided manufacturing. So we need to learn about that, and you need to be aware of it, especially if you're building a CAD system or building any software which will work with CAD system. So that's the broad area we cover mostly in the semester. And then we look at application of these ideas. For example, one question you might ask is that if I wanted to build the hull of a ship from a flat plate of metal, what shape can the hull of the ship be? It turns out back in the 19th century, Gauss had proved a theorem which said that if you take a flat metal plate and want to change its shape without stretching it, and you don't want to stretch it because that will create weakness in the metal. If you want to do it without stretching it, then you have to have Gaussian curvature 0. It's a beautiful theorem he proved back in 150 years ago. And today that theorem tells us what are the kind of surfaces you can make the ship's hull, as an example. And the surface is called developable surface. And we'll learn about it, and it's an example of the kind of things we do. And finally, towards the end of the semester, we talk about other applications, but I'll also talk about how you use these techniques in various engineering problems. We don't go that deeply in this latter part of the discussion. One of the things I do talk about is the problem of linear line and surface fitting. That's linear regression and their generalization. One reason I discuss that a little more at length is that in the recent years, with the advent of big data, these techniques have become more popular. The big data and machine learning and data mining have become popular. I will not get deeply into those subjects, but I will devote one lecture giving you an outline of how they fit, how their techniques are used, and how they fit into this framework. And finally, I work in a computer system area, CAD. I worked in the development of CAD systems in the past. And so I'm familiar with the computer science and computers, evolution of computers. That's a vast subject, but I conclude by telling you where computers are going and where the computer systems are going and how it will affect an engineering student, especially a mechanical engineer of the future. In particular, I will talk about a little bit about multi-core, about cloud computing, about big data, about machine learning, and data mining, etc. Again, it's not going to be covered deeply. It will just be one lecture where we discuss and ask how all of that technology is going to affect the computer-aided design and computer-aided manufacturing and engineering computation in the future. I hope you'll join us in this series of lectures, and I hope you'll have fun, as much fun as I had, learning and teaching this subject. Thank you.